Okay, hello everyone. Nice to be here. In this presentation, I'm going to talk about the Ethereum phone and use it as a case study of a emerging device category, which is called crypto phone. And I want to take a look at this device from the moment we took it out of the box to see if its trust chain can really protect our digital asset. And first thing, some about myself. So my name is Guanxing Wen, and I'm currently a researcher at CertiK. And my mostly interesting lower-level systems of smartphones, electric vehicles, embedded system. And my recent focus have moved towards the intersection between the blockchain and the traditional security infrastructure. So that includes the hardware wallet, the DPIN, or the blockchain code itself. And so the crypto phone is therefore a very interesting target to me. They are not just smartphone, they're not just hardware wallet. They sit exactly at this intersection. So if you want to interact with a blockchain, use some DeFi applications, you're going to need a wallet. And a wallet is basically a custodian of your private key. It signs transactions and broadcasts them to the blockchain. Traditional browser extension wallet is very convenient and very easy to use, but they are not very secure. If the attacker can get privileged access on your laptop or your browser running environment, there's a real chance they can reach the key. The hardware wallet improves the security model. They are managing the key on a separate device, but they are less convenient. You need to carry an extra device, connect it, and confirming every signing operations. The crypto phone tries to solve this trade-off. So you can use the DeFi applications directly on your smartphone, but you don't need to carry an extra device. The claim is that there is some kind of enclave or similar modules that manage the key, so the key never leaves the secure environment. Another aspect I want to talk about is airdrop. So this matters at the end of this talk. Blockchain projects often reward their early and enthusiastic users. So the airdrop is like a lottery money to them. These users may join the community campaign, retweet something, bridge funds, or staking them on the new chain. So all these activities are signals for reward token distribution. And if someone prepays a crypto phone and wait months, even years for delivery, that already signals a commitment to the ecosystem. So they become the natural airdrop targets. And the airdrop money can be sometimes very large, larger than the device cost itself. So our target today is Ethereum phone, also called the Generation 1. Its operating system is called ETHOS, and it's using a MediaTek chipset. From its official documentation, we can see that the private key is simply managed by the trusted execution environment. Well, that sounds straightforward, but there is actually a technical complication. Historically, Ethereum and many other blockchains are using SECP 256K1 to sign transactions. But Android and iOS key systems only support SECP 256R1 instead of K1 with hardware-backed curve. So that means if they want to manage a Ethereum-like private key, they cannot use the key store system by default. Some other products such as Solana phone or Samsung phone, they all have their own custom trusted execution environment, trusted app, to support the blockchain operations. So I want to take a look at the Ethereum phone to see how it does underneath. And to do that, we need to reverse engineering the operating system. I think I first saw the ETHOS in around 2024. Back then, it was DEF CON. Someone was selling a Pixel device running this operating system. But I thought that it was very interesting because it's one of the few attempts that really try to build a blockchain native operating system instead of another wallet on top of Android. But a Pixel with ETHOS is not the same. Now the Ethereum phone has its own hardware, its own boot chain, and its own integration with the system wallet. So we can only know the details by reverse engineering its own firmware. And on a modern smartphone, extract the firmware typically means you need to get root level access, which is not very trivial on a black box running environment. But there is another common route, that is the download mode. So the download mode is very common on phone platforms. So like Qualcomm's Sahari, Huawei's Xloader Recovery, Samsung Exynos, Pixel Tensor, they all have their own download mode. The names may be different, but the idea is basically the same. So no matter what the damage it caused to the flash storage, the BootROM is immutable. So the BootROM can always export a USB interface for you to upload a second stage loader, extending the ability of BootROM, allowing you to read and write flash storage to recover the phone into normal state. If you are new to this area, I would suggest EDL and MediaTek client projects. They are very good resource for you to start with. And previously, I have worked on Huawei and Qualcomm's download mode, and I want to take this chance to explore how MediaTek's download mode and its boot chain work. In the high level, the BootROM is the first code to run. And then it will load and verify the preloader into memory, and then transfer code execution. So this is the normal state. If you want to switch the phone into a download mode, on some phone platforms, you may need to get hardware access, like short a test pin with the ground. But luckily on my phone, on this MediaTek platforms, I can just use a button combination. And so when the phone is powered up, you press this buttons, and it will switch to download mode. And then the BootROM will give you a small time window for you to upload the download agent. Of course, the security boundary would be authentication. So the SLA is around the command verification, and the DAA is to make sure the download agent is authorized by the vendor. But after checking these two flags on this phone's fuses, I noticed both of them are not blown. So that means basically this authentication is not enforced. You can upload any compatible download agent for this phone. And I'm pretty sure you can find a download agent for this chipset and allowing you to extract the firmware. But I would say that it's a little waste of this early access. So that only gives you a static analysis ability. So I want to keep this early access and propagate all the way to the post-boot stage, allowing you to debugging the system like year 3, year 2. So that's all the interesting stuff we try to look at. So we can actually start by like sending the preloader here. The result is that the phone will boot into normal state. This is not that trivial on other phone platforms like Qualcomm. If you send the second bootloader here, the phone will not boot up because the BootROM is using different initialization passes and different boot parameters. So you will have still to patch a lot of things to make it work. But luckily on this platform, yeah, I'm very lucky here, that the phone will just boot it up and it will all the way get into the Android system. So that means we have a very good start. We can put our shellcode, patch something here, and then try to start our patching chain. If we're still dealing with the traditional MediaTek boot chain, the rest of the exploitation will be pretty simple. So we just patch a little kernel from preloader, and then we can just upload any Android kernel. But now the MediaTek boot chain is way much complex. There are many intermediate stages. So if we want to keep this early access, we need to patch most of them. And another requirement is that we don't want to touch the flash storage, because any modification to the flash storage, the boot state, or the analog flags may be consumed by the later bootloader, gatekeeper, keymaster, or the security models. And if any of this state is unexpected, the system may still boot up, but the secure world will refuse to unwrap some keys, and then the Android system may decide that the user data is no longer trustworthy and then initialize a factory reset. And that is something we never want to see. So we actually need a in-memory multi-stage patching strategy here. And also, most of these intermediate stages does not have the preloader's USB interaction. So we need to prepare everything at the beginning. And I call this patching strategy the load-off loader. So the idea is pretty simple. So for each stage, we find a place to put our shellcode and then modify one of the function to call this shellcode. And then when this stage actually executes, it loads and verifies the next stage. But before jumping to the next stage, our shellcode will be triggered, and then our shellcode do the same thing for the next stage, find a place for shellcode and hook one of this function. And so this thing goes automatically all the way to little kernel. So let's say for the next stage after BootROM is preloader. And the preloader is very similar to BootROM. It just initializes more things and load the BL2 and the Genius zone into the memory. So notice that the Genius zone is later at the boot stage. It is actually loaded by the preloader in the very early stage. So if you want to patch something, this is the right moment. And the MediaTek does not use raw images. There is some kind of format, but it's very easy to figure out. So for each partition, there will be several sections. Like the later kernel partition have later kernel, BL2, some certificate, some metadata, and they all start with a 200 hex bytes header. So you can easily extract the content and know where to patch. For instance, if we want to patch the BL2, we will first find a function between the verification and the actually execution of the next stage. And here the patch point function I choose doesn't matter to the boot chain. It just prints some logs there. So we replace this function with a call to our shellcode. And the shellcode for patching BL2 is pretty simple. We just copy the BL2 shellcode into the memory space of BL2. And we've modified one of the functions in BL2, and yeah, and that's done. So let's talk about Genius Zone. I think this is the new module that in the boot chain haven't seen before. I mean, there's a change for the Android boot chain for almost all phone platforms. So previously, Trust Zone is the technology to split the Android into normal world and secure world. And the phone vendors for years, they put their secret services like Gatekeeper, Keymaster, DRM, Fingerprint into the security world to prevent the Android root malware. But there's a problem. The Trust Zone implementation can be very different across chipset vendors. And they are not transparent. They may encrypt it. They're using undocumented proprietary MML registers to protect the physical memory. And all these things make it very difficult for external researchers, or maybe even Google, to audit all these services following the same standard. So I think 3 years ago, Google proposed the AVF, which is Android Virtualization Framework. This new technology is also used to isolate the running environment, but they are not using the ARM Trust Zone technology. They're using the EL2 virtual machine technology. It's very mature on desktop. It's basic page tables, so you know who can access whom. And of course, Google will need support from the chipset vendors. So Qualcomm's EL2 solution is called Gania, and for MediaTek is Genius Zone. And it also gives Android more flexibility. So the Android can create new VMs And like the VM running, I think it's called microdroid, so you can put your isolated apps there, and it will work. And it allows Android to dynamically create new things and don't need any further support from the chipset vendor side. So because we don't know if the private key we mentioned in Ethereum's documentation is using ARM trust zone technology or this new AVF, so we also need to put some backdoor there in case we need to pick or poke its memory. Just like ARM trust zone, Genius Zone is encrypted. And I haven't reverse engineering the lower level of MediaTek before, but I do have done some similar research on other phone platforms. But this time I just copy-paste this code snippet into ChatGPT, and it quickly gives me a 80% correct answer. It tells me that they're using a hardware crypto engine, but very different from other phone platforms. I mean, normally the key being used for decryption is embedded in the hardware crypto engine. But apparently, they just pass the key and IV as parameters. And so the answer is 80% correct. I still need to figure out which one is the key, which one is IV, and big Indian, little Indian, maybe AES, CTR, CBC, and all this, but not too many options. So we quickly notice that the correct answer is whatever we have left here. So for other phone platforms, you can only have an oracle, but for Genius Zone, you can decrypt the firmware offline. But after hours of reverse engineering, I noticed there is actually an open source implementation of this function in the MediaTek client. But there are no code references to this function, so I can only know what it does after reverse engineering this whole preloader. And so if we want to put a backdoor in Genius Zone, it's pretty simple. We can just replace one of this HVC handler with our shellcode. We can just pick one of them that is not critical to the system. And later, we can use HVC calls from the Android side to gain the EL2 read and write and execution primitive. So the next stage after preloader is BL2. And BL2 just loads more images into memory, like the later kernel itself and untrusted firmware. And this time we do the same. We just find a function like this, get timer milliseconds. It doesn't mean too much to the boot chain, so we replace this call to our shellcode. And it will start to patch other images. It also is in the place between the verification and the execution. Then the next stage is untrusted firmware. I don't think we need to talk much about that because it's a very common module in the boot chain, I think, on most of the phone platforms. And to leave a backdoor, we can do the same. Just like Genius Zone, we replace one of its SMC call handlers with our shellcode, and then we can have that backdoor working. So the last puzzle in this patch chain is the little kernel. And the little kernel is the bootloader stage that you can interact with fastboot command. And it also loads the kernel and jump to Android. The problem for this little kernel implementation is that there is no boot command, which caused me a little headache because it's very useful command that you can upload the kernel into memory without touching the flash storage. So our patch has two jobs. First is to bypass the image verification. And second, we have to implement this boot command by ourselves. And this is the patch for little kernel. It's way much complex than the other patches. So here, we replace the original disk reading function with ours. And now the code logic is that when the requested partition is boot, we will copy the data from download buffer instead of reading the flash storage. So that means we can upload the kernel first somehow into download buffer and then just use this in memory. And to do that, we also need to enable the continue command. We need to prevent this download buffer from freed. because other case, the kernel may be overwritten by the following data in memory. And we also need to force the bootloader into the fastboot command mode. And we just replace this two function with a, just let it return 0. And because we don't want to touch the unlock flags as we mentioned before. And there's another bug that actually I think introduced by my patch, because the download buffer is not freed. So later when the later kernel tries to load the modem, it will not be enough continuous memory. So my workaround is just to half the size of this allocation, and it works. So I'm basically doing some optimization of this later kernel. And so after that, we can jump to the Android kernel. And the kernel patch is not in the patch chain we have just mentioned, because right now we can just upload whatever boot images we want. And just be sure to leave a SMC and HVC backdoor there. So let's see how this works. And this is the Ethereum phone. So we will press the button combination to let it jump into the BootROM download mode. And hopefully this works. If not, we have a video backup. OK, so when the phone enters the BootROM download mode, we just upload our preloader patch here. And then the phone will continue to jump into the little kernel mode. And then we flash a non-exist partition. So we only use the upload command, not the actually flash. And after that, the phone will continue booting into the Android part. OK, so to verify that our patch actually works, we can use the backdoor we left in the kernel to gain root privilege. And it works. Yeah. So we have walked a long way, prepared a lot of things. And I think it's time to harvest. Yeah. So the first thing I want to look at is the screen lock. Bypassing screen lock in Android system is very sensitive, and it's more critical for a crypto phone, because the screen lock is basically the only thing that prevents you to use the digital asset inside the device. And if you try to analyze this kind of logic, the usual way is to follow the credential. So you start with the Java level framework, which is called lock settings, and then you will jump into the native level gatekeeper, and finally you may end up in trusted zone or strongbox depending on the implementation. So sometimes the vendor may implement some extra stuff in the Java framework, and they may use the password-derived value for some other purposes, and that will actually give you a brute force primitive, and you may not even need to interact with the gatekeeper in trusted zone, and then you can just brute force. But you can only find this kind of issue by walking the whole path. So let's start with the Java framework, and then our pin entered on the screen will be first stretched with AScript, and then char hashed. And all the parameters for these two algorithms can you find from the password file that is created together with the pin. And then it will jump to this hash will be passed to the native level. So normally on other phone platforms, there will be a implementation, something shared library being loaded into the gatekeeper services. But on this phone, I did not find any. It's not using MediaTek or Qualcomm or OPT, none of them. The only thing I can find being loaded into memory is the soft gatekeeper. So from this name, it's already very suspicious. So let's see what it does. So I have reverse engineered other trust zone-based gatekeeper, and I'm very familiar with these two functions. I'm pretty sure they should be implemented in the trust zone side. But now they're just being implemented in the shared library. And they also have some tricks here, like the is hardware-backed function is being hard-coded to be 1. So that means if you check from the user mode, it will always give you the answer that the phone is using trust zone or strongbox. And another thing is the get password key. This function normally should return a hardware binded key so that the gatekeeper algorithm will have the hardware involved. That means you cannot brute force the pin code offline of the device. But now, as you can see, the key is not being used to calculate the signature. So that means every parameter we need can be retrieved from password file, and there is no hardware involved. And to conclude, our pin code is first stretched with script, and then char hash, and then script again, and all the parameters can we find from that password file. And that means we can brute force the screen lock of the device with like a Python script. So let's see the demo. Here we first grab that. No. We grab that password file from the device, and then we just write a script to brute force using the algorithm we have just described. So for this demo purposes, I'm not using a very complex password. But even though it's just maybe 6 digits, so on a high-end server, it will take no longer than 10 minutes. So the password should be Let me check again. Okay, it works. Okay, so following the same path, I started to analyze how the private key is created and stored in the system. And again, they are using a software, and this time pure software implementation of the key store system. So the content you stored inside the smartphone is not actually encrypted. It's just serialized and stored inside the database. So that means typically on other smartphones, they're using this same storing structure. You can see similar things here, but the only difference is that block entry is encrypted. But now, after reverse engineering the system wallet, I know the field is called P256 ETHOS, and the private key can be retrieved from the blob entry directly. And to understand how this private key is actually being used, we need to get some basic knowledge of smart account. So traditionally, the private key is used to sign. Okay, I think. Okay. So traditionally, the private key is to use to sign the transactions. And so the private key can decide the public key, and the public key can derive the user account address. But right now, they are not using this traditional external account strategy on the smartphone. They're using a smart account, which is basically a smart contract on chain. So the address will not be changed. I mean, the account address is a smart account address. And you can store any public key there, and you can put any algorithms to verify this public key. So that means the smart account can support more than SecP256K1. They can support SecP256R1. So that's the trick they do to support. Actually, they're using software implementations, so it does not matter. But I mean, if they want to really use the key store system, they can do this by using the smart account. And so to verify the ownership of this private key, we can derive the public key from the private key and then invoke the on-chain smart contract to know that we actually own that. So let's see how we can verify that from this. First, we find this database. Actually, this database is stored inside the D storage. So it's not in the C. On Android, the C storage can only be retrieved by unlocking the screen. But this thing is stored in D, so that means we don't actually need to unlock the screen to find the passcode, and we can just grab this database. Okay, so because we already know the key field is P256, and so we can find its blob entry, and then we can grab that private key. And there is some kind of format here, so we need to calculate. We need to grab the private key from this format and then calculate the public key. So the x coordinate and y coordinate of this public key is here, and the system wallet address can only be found from the device. And so as you can see, the account address is started with something 32FD. So we can call this contract using the chain explorer, and this account is live on base chain. So we will use its owner public key function here. Type in the coordinate. Okay, so it returns true. That means the private key we have just grabbed from the system is actually controlling this system wallet. Okay, so the last thing I want to talk about is the airdrop. As mentioned before, the blockchain projects will reward these crypto phone users. But how do they verify their identification? I'm pretty sure there are many other ways to do that on other crypto phone platforms. But on this one, they are using the IMEI and the serial number as the identification. And the IMEI hash is sent to a backend server which is owned by the phone vendors. So of course they know all the combinations of this IMEI hash, and they must have a list. So after you talk to them, they will give you a signature. And then you can invoke the on-chain contract with the IMEI hash together with the signature. And the on-chain contract just need to verify the signature is correct, and they will give you the airdrop money. So in this model, you need to make sure the IMEI and the serial number are really secrets that nobody can gain. Otherwise, they can steal your money. But in reality, as you can see, this is the whole package you can get after purchasing this crypto phone. Both of these two values are printed on their label. So you may say it only affects the delivery guy or the factory workers, but people do sell this thing on online market because they don't know what the price behind these two numbers. So they may just give you the picture of that, and you can just steal the money of this potential user. So if you are using a model like how many interactions do you need from this user, 0 click, 1 click, I think this is maybe a -1 click. They're not even shipped to the real owner. And so that is pretty much all about my presentation here. I hope you like it. Thank you.